Hello, Algebra 2. Today we're going to talk about 12-5, the normal distribution. This is another statistics and probability section that we're going to talk about. Our objective is going to be to distinguish between positively skewed, negatively skewed, and normal distribution curves. We're going to do that by looking at curves, but also by looking at data and being able to create curves out of the data. Okay. The second part of our objective is going to use the empirical rule to solve problems involving normal distributions. So let's start with the first set of notes. Let's talk about normal and skewed distributions. Normal and skewed distributions. So when we talk about distributions, we're talking about how data sets up on a graph. We're talking much more visual than anything else. Okay, so a normal curve, and you have seen this before, and you've seen it recently in something very important, and we'll talk about that in just a second. Let me show you what it is first. A normal curve looks like that, okay? And it's got its center right there, and then it's got these partitions sort of there, and a little later we'll talk about what those partitions mean. But for right now, I just want you to see it, okay? So that's a normal curve. A positively skewed curve looks like this. It looks like that with, and that line that I'm drawing is where the mean is, where the average is, okay? A negatively skewed curve looks like this. It's the opposite of a positively skewed curve, of course. Why wouldn't it be? So that, and I've never come up with a good way to be able to remember positively skewed and negatively skewed. The only thing I can ever think of is that they're the opposite of what I would expect them to be. If I see positive, if I see the word positive, I more expect that to have the hump on the positive side, and then I have to remember, oh no, wait, it's exactly the opposite of what I expect it to be. So I don't know. You're going to have to come up with your own way of figuring it out and being able to know the difference between them, okay? This is going to be an exercise in metacognition and understanding how you think and coming up with a strategy for the way that you think. So let's do an example, and we're just going to be concerned with how do you know the difference, especially when you're looking at data. Okay, so example 1 is the data positively, negatively, or normally, or normal? I've left out the word skewed in there because I didn't feel like writing it. getting lazy. So here's the data: 100, 120, 110, 100, 110, 80, 100, 90, 100, 120, 100, 90, 110, 100, 90, 80, 100, and 90. Now, I don't know what this data is, but the beauty of this is it doesn't matter, okay? All that matters is that the data is sitting there. To answer this question, we don't have to know what the data is for, okay? So let's do this. Let's graph this. And the way we're going to graph it is I'm going to have a mark for, not like that. I'm going to have a mark for 80. I'm going to have a mark for 90. I'm going to have a mark for 100. And I'm going to have a mark for 110. And I'm going to have a mark for 120. And I'm trying to keep these marks evenly distributed and try and keep the amounts pretty even between them. And over here, we're going to count, okay? And so it might do us good to know minimum and maximum numbers here. If you look, I've only got 2 instances of 80, and I think that's the least amount. I got 2 instances of 120 also. So I'm gonna count by 2s. 2, 4, 6, 8, 10. And if I have to go above that, I'll go above that. But for right now, we just want to count them. Okay, so 80 and 80. That's 1, 2. So I'm going to create like a bar graph here just to keep track real easily. So there's 80, so I've used up my 80s. Do I have any more in there? No. So let's count the 90s. 1, 2, 3, 4. So 4 90s, so 2 80s, 4 90s. Don't think I'm missing any, am I? 1, 2, 3, 4. Okay. Let's count the hundreds. 1, 2, 3, 4, 5, 6, 7 100s. So that'll be about there. 7 100s. 1, 2, 3, 4, 5. Oh, did I miscount? 1, 2, 3, 4, 5, 6, 7. Okay. So 7 100s, and then the 110s. 1, 2, 3, just 3 110s. So 3 110s. And then finally the 120s, and there's 1, 2 of those. So I didn't cross off my 110s. So 2 120s there. So now the idea is that if I look at this data And if I start with a curve, and you see if I draw a curve connecting these, how does it look? What does that curve look like? Okay, and that's what we're trying to figure out. Is this curve, does this curve look positively skewed? Does it look negatively skewed? Does it look normally distributed? Which one? And if you look at this, so let me remind you, a positively skewed one looks like that. A negatively skewed one looks like that. And a normal distribution looks like that. And this looks very much normal, right? I hope everybody can see that. It's pretty darn close. It's pretty normally distributed. Okay, so that's using data. Now let's talk about normal distribution, and let's talk about why it's so important. Okay, there is a rule. And the rule is that over a long enough period of time, randomly generated data will always fit itself to a normal curve. And you will begin to see this if you've been following the news about COVID-19 and that sort of thing, and you've been following like flatten the curve and that sort of thing. You will see that as they keep generating the data for it, especially if you look at the worldwide numbers, you want to look at the largest numbers possible. Okay, the smaller the number, the less probability that it'll be normal. But if you look at real big sets of data like the world data for this, you will see that we're starting to create a normal curve, a normally distributed curve. We have something called the empirical rule. And this is for normal distribution. Okay, this is for normally distributed data. And the way this works is, I'm going to make a nice big normally distributed curve here and try and show you all of this within that curve. So remember, I had these cuts before, and the middle cut is the mean data. Okay? And then we're going to have another cut, and it's going to happen right about here on both sides. I'm going to use that symbol again for standard deviation. Remember, we talked about standard deviation in a previous section. We calculated it. Now I'm going to show you exactly where it goes and how it deals, okay? So from here to here is one standard deviation of distance, and it's a negative standard deviation. From here to here is a positive standard deviation away from the mean. So when you get to here, you've gone one standard deviation away from the mean, either in the positive direction or the negative direction. That is, the numbers are either going up or down. Okay. Then there's another cut here on both sides, and this is 2 standard deviations away in each direction, positive and negative. Let me put that somewhere else, though. And then there's actually a third cut way over here, which is 3 standard deviations away in either direction. And what happens is we get percentages as we go, okay? So here is the way the rule works, and these are approximate. 68% of the data is within 1 standard deviation of the mean. Okay, so that means from here to here, everything in there counts as, that is, all of this is 68% of the data. Which means if we wanted to split this up amidst the 2, we'd be talking 34% here and 34% there. Okay? And then, so then you have a breakdown of percentages that are within that distance. The next one says that 95% is within 2 standard deviations of the mean. Okay? So all of it from here to here makes up 95% of the data. So if you do 95 minus 68, you have to borrow, and then that'll be 7, that'll be 2. So we're talking 27% between here and here. So we have to cut that up into 2 pieces here. So 27 divided by 2, half of 27 would get you 13.5% in each slot here, right? So if you take all of these percentages and add them up, you'll see that you get 95% because you're doing, when you add these 2 up, you get 27. When you add those 2 up, you get 68. And 68 plus 27 is 95. And then the last rule is that 99% of the data is within 3 standard deviations of the mean. Okay? So 99 minus 95, I don't really have to write that, but so there's 4% left here, so if we divide that evenly among the 2, we get 2% and 2%. And then all the rest of it, that other 1%, is distributed as 0.5% on each side. So this gives you a really good way to break down the percentages of everything going on. Okay? And we're going to use this and the idea that if you have enough data, if you have big enough populations, big enough sample sizes, whatever, that everything is normally distributed. You can just assume that it's normally distributed because that's the way things work. So let's talk about our second example here. Example 2. Heights of basketball players are normally distributed with the mean, remember x bar can mean the mean, the average, the mean being 6 foot 1 inches with a standard deviation of 2 inches. Okay? And there's 2 parts to this. Part A, what is the probability that a player selected at random, and remember at random is an important thing with normal distribution also. I don't know if I've made that real clear, but it's random data is normally distributed. Data that isn't being manipulated in any way is normally distributed. If well, I'll talk about that in a second, but essentially, if you were rolling two dice and adding them up and keeping track of all the data, if you roll enough of them, you'll get the normal distribution, unless you're using cheating dice, and that would be the way to know that the dice are that the dice are loaded. Would be that you don't get a normal distribution because all of a sudden it's not random anymore, it's being manipulated. So what is the probability that a player selected at random is shorter than 5'9"? Okay. So let's look at a new board here. So we're looking to be shorter than 5'9" tall. And let's draw a nice big normal distribution because we know it's normally distributed. And let's look at where things are. So we need the mean, the average. The average was 6 feet 1 inch. We also know that the standard deviation is 2 inches. So when I go this way, I go 2 inches down. That is 2 inches in the negative direction. If you go 2 inches shorter than 6'1", you get 5'11". And if you go 2 inches taller than 6'1", you get 6'3". If you go 2 standard deviations away, you go another 2 inches shorter, so 5'9". Another 2 inches taller, so 6'5". And then you could do one more. 2 inches shorter would be 5'7". 2 inches taller would be 6'7". So that's the way it looks, and then we can use these, there's 34% here, there's 34% here. I'm going to look back at my other one, 13.5 to and so on. Okay. So 13.5% here, 13.5% here, 2% here, 2% here, and then 0.5% there, and 0.5% there. Okay? So, let's go through the scenario one more time. Remember, this is part A to this. Let's go through this scenario one more time. And the scenario is that given this distribution, we want to know the probability that we get at random a player shorter than 5 feet 9 inches. Okay? So let's see how that works. Well, let me find 5 feet 9 inches. There's 5 feet 9 inches. And what are the chances that when I at random choose this person that they are going to be 5'9"? Well, there would be a 34% chance if I was